if you haven't been here last time, my name is Eszter. I'm a UKMT volunteer and also a teacher in London. And what we are going to deal with today is graph colorings. Now, what graph colorings is basically a graph. It's quite actually easy to catch up even if you weren't here last time. A graph is a collection of points connected by some edges. And basically, if we want to color a graph, usually, if we want to color the vertices, usually we want to color the vertices some color, such that two neighboring vertices are not the same. So they are neighboring if they are connected. So like this wouldn't be good because they are both orange. But like if I change this blue, then for example, this one could be orange. Because even though they are next to each other, they are not connected, so they are not neighbors, even though like on the plane they are pretty close to each other. Now we are dealing with a special type of graph, so actually I think I've written it like a couple of times here. It's a simple connected planar graph, which basically it's quite simple what it means. Simple graph means is that we don't have like fancy things, like we wouldn't have two edges between the same pair of vertices. So that's like, we don't want to do that. So simple graph means we have vertices, and if two things are connected, they are connected. If they are not, they are not. Now this word connected means that there are no standalone edges, standalone vertices, or that we don't have two parts of a graph. So if, for example, if I would have this, what I have on the screen now, that's not really good because I have two components. Now this is not connected. If like there's an edge there, it's all connected. So we are dealing with connected graphs. And the last thing is planar. That's the hardest thing in it, but actually it means that you can draw this graph without actually the edges crossing each other. Let me show you an example. Now, if you have this graph like so, if you draw it like that, the two edges in the middle cross each other. But actually, if I was a bit better, I could have, instead of this in the middle, that edge, I could have drawn that edge like that, which is absolutely fine. They are still connected and it's in the plane. Now, I can't always do that. There are some graphs when you can't do that. So, for example, a simple example of a graph that you can't write in a plane, can't draw in a plane, would be a graph where this graph, you can try to fix it, but no matter like this one you could like move to the outside, and that one you could move to the outside, but actually you can't fix everything. So if you have this graph, that will always have some edges crossing if you draw it in a plane. That's why that graph is not planar. So we are only dealing with planar graphs today, and in the top, you don't need to remember these formulae, but I have a couple of formulae which we have used previously, which is actually quite simple. V is the number of vertices, E is the number of edges, and F is the number of faces. It means like how many regions does this graph cut the plane into. So for example, if we consider this graph, it cuts the plane into two parts. It's going to be like this part and everything outside. And if we do vertices minus edges plus faces, it's always going to be 2. And then we actually proved two more quite important things, which is if 2 times the number of faces is less than, 3 times the faces is less than 2 times the edges, and 3 times the vertices minus 2 is always at least 6. And what we proved for, I'm not going to repeat that proof, but you can watch it on the video, which is in the UKMT's YouTube channel. Basically, if you look at a simple connected planar graph on at least 3 vertices, there's always going to be one vertex which has at most 5 neighbors. And actually, that important fact we used to prove that you can color every graph with 6 colors. So actually we did the 6-color theorem last time, and our argument goes, well, I'm checking it for 1, 2, 3, 4, 5, 6 vertices. Up until 6 vertices, you can certainly color it with 6 colors because you have a color for each vertex. and you say, okay, let's say I can color everything up until a certain number of vertices, like k vertices. Now I can color, if I have a graph with k plus 1 vertices, that graph is going to have one vertex, which has at most 5 neighbors. If I consider the graph just removing that vertex, I can color everything outside, and I can just pick out of the 6 colors, I can pick one color for my vertex in the middle. And that was our argument. What we are going to do today is improve that argument. Exactly, it's actually not super difficult, but we need to do a couple of subtle things to prove the theorem to 5 and maybe 4 colors. We'll see. Okay. So actually, we are going to, for the 5 color theorem, strategy is going to be basically same as for 6. So this is what we call induction on the vertices. Oops, vertices. So we say we are checking for a few, and we can color everything with 5 colors up until it only has like 5 vertices. So up until 5 vertices, it's quite easy because we have, again, a color for each vertex. So it works for v less than or equal to 5, definitely. And now we suppose that it works for, works for v equals n. And we want to check, we want to show that it works. Show it works for v equals n plus 1, if it works for n. So basically that means if it works for 5, it works for 6, and if it works for 6, it works for 7. So actually if we show this one step, then it's going to work for everything. Now, I'm going to go to a new screen. So basically, our most important fact that we are using is that there's always one vertex with at most 5 neighbors. So what could happen? If I have this graph with n plus 2 vertices, sorry, n plus 1 vertices, hopefully not, n plus 1 vertices. This is my vertex with at most 5 neighbors. And actually, if it only has 4 neighbors, then all is good, right? So if it has 4 neighbors, then they have 4 colors at most. So we are happy. We are just gonna basically what we have there is outside. We remove this vertex, color everything on the outside, and then just pick an appropriate color for this one. So our correction step is working. Now the same thing would work if this has 5 neighbors, because there's not always one with 4 neighbors. And maybe what could happen is like we have 2 vertices of the same color around it. So that would also be quite good, because then we could just like pick the last color. So what do I want? Red or whatever. We could just pick one color. So we have one color left. So actually, where it can go really, really wrong is if we have one vertex which has 5 vertices, so we picked 5 neighbors, so we picked our correct vertex, but all the neighbors are different colors. So actually, I'm going to, can I actually, oh no, if I do erase, it erases everything. Sorry, all went away, but I'm going to draw now correct picture. So we have this special vertex. It only has 5 neighbors, but they are all different colors. And sorry, I think it might be a bit annoying, but I think it's really worthwhile just drawing out the colors, because then you can really see what's happening. So strategy is we want to shuffle around these colors and basically like change one of the greens, or like change the green to an orange or something like that. In fact, we can try. We could change the green to an orange. But what we have to be actually careful about, if we change the green to an orange, this is just one segment of the graph. The graph continues quite a lot, like all around here. The graph might continue, we don't know. So actually, what could happen is that this green vertex there has, I wanted to do that with black. So it could have multiple neighbors. Some neighbors might be blue or whatever, but some neighbors of that green vertex might be orange. Maybe this one. So actually, if we decide to recolor this green vertex orange, because basically then we would free up the orange and our goal is to have the center green. Now if I recolor that orange, then I must change all its orange neighbors. I want it to have 2 orange neighbors. Then we must change all the orange neighbors. I'm going to change them. Well, it's quite sensible to change them green. So we are just swapping it. But now I think you realize that the problem is those newly green bits, newly green vertices might have green neighbors because they were orange. So it was okay for them to have in the past green neighbors. So for example, if this guy had a past green neighbor, I'm going to swap it to orange. And I'm going to continue like so. So I'm always swapping. Now, there are 2 things which we are quite concerned. Now, one thing is, what if I never stop swapping? So what if like I go in a circle and then like one vertex is green and I change it to orange and I go around and change a lot of other vertices and I come back and I color it to green again and like I never stop. So that wouldn't be really ideal. I can't do that. That's not fair and not possible. So actually, good news is that's not going to happen. Basically, let's see what would happen if that would happen. I'm going to do a couple more vertices like so. So let's say like so. I'm just going to quickly color them. So originally it was orange, then originally this was also orange. Now, and then this was originally green. So let's see how it could happen that I have this infinite circle. So how would I need to actually recolor the same vertex twice? Now, if I go around with recoloring, so I recolored this vertex there, I recolored that orange. So if I go back and I'm going to recolor this green, and then I go ahead and I'm going to recolor this orange. And then I go ahead and I'm going to recolor this green. But actually, like what would happen for something to need to be recolored again? Say I want to create a scenario when this needs to be recolored again. So that means that for us to need to recolor that orange one there, it needs to be the neighbor of a newly greened vertex, like so. Because it's always only newly green vertices, neighbors of newly green vertices will be the new color. This is a problem. So if this would happen, then I would need to recolor it. Oh no, right, sorry. It needs to be the neighbor of a newly orange one. Sorry, I was talking complete rubbish. So actually, now this is newly green. So actually, its green neighbors need to be recolored orange. So actually, that would mean that this color would need to be recolored. But this is what can't happen. So this is when this would be recolored orange. And this would never happen because basically, if you look at the original color they had, they were both originally orange. So actually, it would mean that we have what's called an odd cycle. It has like it's a pentagon, sort of, or it could be anything with odd edges, odd number of edges in a cycle for it to happen. And it wouldn't be originally valid. So actually, it's never going to happen. So that's quite good. If we do this, after time, we are going to stop. Now, the other problem is, if we believe this actually stops, that's pretty good. So we successfully changed our green vertex orange, which is awesome. Now, the other problem, unfortunately, you can't send comments. The other problem which could happen is if actually this orange would change to green, which could happen super easily. Like if I'm going to do, so this was originally, Well, actually, these two could have originally been connected, right? So when we recolored this top one orange originally, then that means that we recolored this one green. So we are back on square one, which would be a problem. Now let's see what our options are. Either, so that is a valid problem. It could happen. We have an example where this happens. Now, basically, what we could have, if it doesn't happen, if our original orange stays orange, then we are done. Then we can actually just color this middle one green, and then we are happy. So if our original one orange stays orange, we are done. We are actually almost done if the original orange changes to green as well. Basically, this chain, what we've done, this orange green situation, has a name. It's named Kemp chain after the mathematician Alfred Kemp. And this is quite useful because we've proved that if we are not able to change the color of the green to orange, what we can do, what's going to happen? That means that there is like a green orange chain, a chain around the yellow. So basically that yellow is sort of entrapped by the chain of green orange. It might be like more greens and oranges in between, but basically it's entrapped. And the reason why that's really good is now I'm going to change the yellow to red. And what happens? I'm doing the exact same thing again. I'm changing it to red. And then obviously if it would have yellow neighbors, I'm going to change it to yellow. Sorry, if it had red neighbors, I'm changing them to yellow now. Like so. We know that this is going to stop at some point, so we realize that it's not possible for it to go on forever because everything will only be colored once. And also, it's not possible that this red, this red in the bottom, our original red, is going to be changed. Because basically, this yellow is protected by a chain of oranges and greens. And because our graph is planar, so we can't have this, like it can't go like that. Can't cross an edge because it's a planar graph. We don't need to worry about that. So actually, we can definitely change the yellow into red without recoloring the red to yellow. And that means that we can color our center one yellow. And actually, that is the proof of the 5-color theorem. So we can always, if we have a 5 coloring of a smaller graph, we can just always add and add and add a new vertex and get everything. Does it? Can I just like an indication of hands as to how much it makes sense? Can you just do a hands up if you're happy with this? Okay, cool. Thank you. Okay, so brilliant. Okay, that's quite good. Okay, so that means we can go on to 6 colors. Sorry, 4 colors. I thought like 5, let's do even better 6, but actually the even better, but obviously with the 4-color theorem. And this is the famous theorem, isn't it? So I suppose like most people heard about the 4-color theorem, very few people heard about the 5-color theorem or the 6-color theorem because they're not that fascinating. But the 4-color theorem is really fascinating because that's definitely the best we can do. So we've already seen that 3 is not always enough. Let's just super quickly show. So if we have a graph like that. Thank you very much, Shona, who has just posted you can send questions to our email afterwards, or also just to reiterate again, it's definitely not in the school syllabus, so don't worry, don't panic if it's a bit complicated. And again, the 4-color theorem proof is going to be quite similar to the 5, so I think it's going to make more sense. Even the 5 will make more sense after the 4. Now, what I've just drawn in the side here is something that can't be colored with 3 theorems. So we can definitely know that we can't do better than 4. So 4 is the best, which is quite good. So our strategy is going to be the same. So we are going to do induction again. So we are going to say induction. So let's suppose it's okay for, well, now we can only suppose it's okay, obviously 1, 2, 3, and 4 vertices. That's easy because we have 4 colors. So good for vertices at most 4, and suppose works for n. So same sort of story. And now we want to find a configuration for n plus 1. For v equals n plus 1. Now, we have a bit more cases to consider, but actually not much. And we are going to use this idea of camp chains, so they are going to be super useful. Now, when I said we know that there's going to be always at least one vertex with at most 5 neighbors, we still need to work with 5 neighbors. Now, what could happen? Let's see. If there was a vertex with 3 or less neighbors, then it would be super easy to color that vertex because it has 3 or less neighbors. So we can just color everything and then pick an appropriate color for the last one. But actually, now we need to, I'm going to label it. Now we need to consider the case when that vertex has 4 neighbors. Because if it has 4 neighbors, then either they have, like, some of them share a color, so they only use 3 colors, in which case it's obvious. But it could happen that actually a vertex has only 4 neighbors, so we don't have a 5 neighbor vertex, we have a 4 neighbor vertex, which is possible because our theorem only proves that there is at least one vertex with at most 5 neighbors. So actually we could have this 4 neighbor situation, or we could have a 5 neighbor situation, which would actually work like, so if you have 5 neighbors, imagine now we suppose that if we remove this graph, everything else can be colored with 4 colors. So if you have 5 neighbors, those 5 neighbors are going to be colored with 4 colors. So I'm going to do 5 neighbors. And actually we are going to have 2 situations of this. So I'm just going to draw it while I have the black pen. Because we are only going to have 1 color that's used twice, and the other 3 colors must be used once each. So which colors should we have? I want to use the red. So what would happen is that actually it's going to matter that the vertices that are the same color, they could be next to each other. If you are just like looking at the neighbors in order, maybe clockwise or something, or they could be not next to each other. Luckily, not next to each other can only happen one way, because like it doesn't matter if it's like the point I colored or the other point next to it, because that's just symmetry. We can just flip it. It's the same graph. And then everything else is just going to have, so we are going to have an orange. Also, it doesn't matter which ones are orange, but I just want to give them a color. We don't have a yellow. I just want to give them a color so that we can talk about them. Which one is the rest? Green. And actually, cases 1 and 2 are going to be quite simple. They are going to be literally the same as it was for the 5-color theorem. Actually, I'm going to stop here really just for 3 minutes. Unfortunately, there is not many ways you could send the solution in 3 minutes, but I think it's worthwhile just have a think about how you would solve them. And I think 1 and 2 you can definitely do with the same idea. And 3, it's very similar. So let me just give you 3 minutes. Okay, I completely appreciate that this wasn't enough to write down any proper proofs or anything, but hopefully it just gave you a chance to think about what happened. And I'm sure if you would be like in a classroom or something, somebody would just say, "Well, we can do. Let's look at case one." It's literally the same as in the previous case. We can, let's say I don't like red. I want to change that red vertex into blue. It's quite important we pick the blue, not any of the other two. Because basically, let's see what could happen. One thing is I can use this method, the camp chain method, and basically change this to blue and then all the neighbors to red, etc. And they finish it, and this blue remains untouched. So then this is blue, and this is blue. They are untouched, so I can swap the middle one to red, or just color it to red, and I'm done. But the other thing that could happen, which would be the unlucky situation, if say I'm going to do how many? So that's blue, that's going to be red, that's blue. Like so, for example. And it could be that this is red, that this blue and this red is connected with the blue, red chain. And what that's going to mean that actually if I swap the red to blue, then the blue swaps to red and I still have a blue and a red, and I'm not really happy. But then what I can just simply do is I can do a swap between the oranges and the greens, well, not all of them. I want to swap this green to orange, and then neighbors, etc., get swapped. I do the whole process to get a good coloring, but I can be certain that this orange won't be touched because they can't be connected. So that's actually really good because now I can end up coloring my vertex there green. So it can either work if you don't get a red-blue chain, then I'm changing it to red. If you do have a red-blue chain, then I'm changing it to green. And the good news is the same idea works for part two. Because in part two, or the situation two, I'm going to do the same sort of idea. But now we have two reds. So my original like instinct would be, and I suppose it makes sense, like I don't want to change the reds because that would be quite a lot of hassle changing the reds, right? So I'm going to change like some of like another color. And we also observe that it's quite good if the colors are not neighboring because then we can do this entrapment of the other color between the two, between in a camp chain. So we can entrap that. So I think that lends itself the idea to having like an orange green situation there. So let's swap the oranges and the greens. And again, best case scenario, I can just swap my greens, like this green, to an orange, and the orange doesn't get changed, in which case I'm sorted. Or it does get changed, so this is the worst scenario. So this would be an orange, this would be like so. Maybe they are connected in a chain like so. But then I can do literally the same what I've done before, except before I changed the green to the orange. Now I'm changing the the blue to the red. And this blue can't be connected with any of the reds. So actually, I'm done again, because then that's going to become a red and we are going to color the last one blue. And it's quite interesting. The same thing would work if I would have like even more reds on that direction. But luckily I don't. Now question 3 is much harder. So pay really good attention because it is actually quite tricky. But you can absolutely understand it. So what I'm going to do, again, is the same sort of idea. I want to leave the reds, so I want to change everything else because I have 2 reds. So if I change a red to another color, that's not really useful. I would need to change both reds to another color. That's more work than changing just one red to another color, isn't it? So I'm going to change other ones. But also, previously we observed that it's quite useful if you are doing a color change with colors that are not neighboring. So in this situation, picking the orange-blue swap, like trying to recolor the orange into blue or the blue into orange, it wouldn't be like that good. Or at least previously what worked is that we didn't change neighboring ones. So actually, what would be sensible based on what we've already done is changing maybe the green. Well, definitely one of them needs to be the green, and let's change it with the orange. Now, easy situation. If I can actually swap my green to an orange without the orange being swapped in the process, then I can just color the center one green. But obviously, in mathematics, we need to look for the hardest case. So it could be, I'm just going to do a short chain like so. It could be that we have a green there, an orange there. So we have a cam chain, a green-orange cam chain. And basically, what would happen if I would swap the green to an orange, then the orange would swap to a green. So I'm like, not better off. It doesn't matter which way. So let's just leave it there. I'm going to say, okay, green, orange didn't work. Don't despair. I'm going to do a green, blue, because that's the other one which seemed good. And if I can change the green into blue without the blue changing to green, then again, I'm really good. And the center one is going to be green. But what we should look for is the worst case scenario when we actually have a blue-green chain. So what would I need? This would need to be green and this would need to be blue. Obviously, this chain could be longer as well, but this is sort of the simplest scenario we could have. So actually, that wouldn't work either, because if I would change the green to blue, then blue would change to green. So I'm not better off either way. But actually, if you look at this graph, what happened is we entrapped the two reds. Both reds are entrapped in a way. So the top red, let's deal with the top red first. It's entrapped in a blue-orange cage. What it means, if I would want to swap the top red to blue, I'm going to do blue, so top red to blue, then if I would do the whole process, I couldn't reach that blue because I can't cross edges, right? So I'm actually quite good because I can change the top red to blue. And I can also change the bottom red. And the bottom red is entrapped in a green-blue cage. So actually, I will want to change it to orange. So I'm going to change it to orange. And again, if I do this process, so if I change everything around it, which was orange to red, etc., it's still fine because that other side orange, like that other orange, is not going to be affected because it's a planar graph and edges can't cross. They can't come out of the cage. Like it could be a bigger cage, but I still couldn't come out. So actually, now we have two blues, two oranges, so the middle one is going to be red, which is, in my opinion, quite surprising because who would have thought that we get rid of two reds? Well, we have two of them, so it would have been like easier to get rid of another color. And that's it. The sad thing is, well, actually, it's quite hard to understand. But are you guys convinced? Are you generally happy with this? I'm gonna actually do a super short poll. Bear with me. Almost there. Yes or no? Are you happy with the proof? Sorry. And I'm starting it now. Ooh. So we have, you can't see how these move, but we have 27 people right now. Well, we have quite a lot of people who are happy, quite a couple of people who are unhappy. Let me show you. Some people didn't decide, which is absolutely fine. So actually, those 5 people who didn't like the proof, it might be that I just explained it horribly, but it might also be that they spotted the mistake. Because the thing is, when Alfred Kemp actually published this proof, everybody thought, okay, awesome, we've solved the theorem. Turns out, no, it's actually not a proper proof. It's a proper proof, it's just there is a mistake in it. And it took people 11 years to find the mistake in the proof. So if you didn't find the proof in the 2 minutes if you didn't find the mistake in the 2 minutes I gave you, then you're still absolutely really clever, because it's quite hard to see what the mistake is. But actually, we are going to discuss why this proof doesn't work. Let's see, I'm gonna close the pool. Okay, so I'm going to do a bigger situation. So right now in this question 3, actually part 1 and part 2 of the proof, actually those work. Those are fine, they are good. But if you look at the third situation we had there, what goes wrong is that in itself, it's true that we can do the green-orange entrapment and swap that inside red to blue. It is also true that we can do the green-blue entrapment and swap the inside red to orange. But the problem is, the two of them, if we do one, that's going to have an effect on the other. And I'm going to show a construction because, well, wish me good luck. Now, basically, what we are doing, it needs to be much bigger. Actually, it's not going to be too much bigger, but let's see. So we have our original situation. We have our reds. What did we have on the top? Was that the orange? No, there was the green. I just want to keep the same color so that we have I think this one was the blue. And this one was the orange. So actually, we know that how we started is there's going to be a chain between the green and the orange. But if the chain is quite small, then yes, it is true that our red can't escape, it's entrapped. But what could happen is that actually we have a much longer chain, and I'm going to draw a bit of a longer chain. So that would be orange, this would be green, orange, green. Hopefully that's going to be, yes, that's going to be long enough. I'm still trying to make it reasonable sized. So like so. And then this is still simple enough. Bear in mind that there could be a lot of other vertices in this graph that are just not drawn in yet. Now, we also know there's going to be a green-blue path. And this is where the tricky bit comes. Because what could happen here is, look, I'm going to do the green-blue path, like one person, like previously we imagined it goes like so, around. And it's going to go around, but actually it could go like so. So we want to have a blue, and then the next one needs to be a green, but it could be this green. And what it could do, we could sort of peek inside. Oh, sorry, the edges are still black. So we could peek inside, and like it could come in there. And then it could go outside again, and I'm going to do like another, oh, sorry. I like doing the edges in black. That's going to be a blue again, and then I'm going to do, okay. So that's going to be a blue, and it's going to be a green. So actually, what's happening in this situation is that our green-blue cam chain went inside a green-orange chain. Why is this a problem? Let's see if we have this situation. What's happening? So we can't swap the green and the orange because then they would just swap and that wouldn't be helpful. And we can't swap the green and the blue because then they would just swap, so it wouldn't be helpful. So what we want ultimately is to recolor our reds. So actually, the top red, right? The top red, I'm going to be recoloring. What do I want to recolor it? Blue, because that's what that red now got entrapped, like encaged in by this orange-green circle. So that red is in the orange-green circle. And it's absolutely true that I can't go in and modify that blue there. But what could happen, possibly, is that I can modify this blue, because now that blue chain went there. So I'm going to do that. So what would that mean? Well, I can add as many edges as I want, obviously, as long as they don't cross. So if I would do that, then this would be, I'm going to cross out and do the new color after the coloring. And then I'm going to say, okay, then if this would be red, then I sort of like, you know, like that chain got ruined. Because basically, our original idea was, so I successfully recolored, by the way, the top one. So I recolored the top red into blue without that blue becoming red. But now I want to recolor the bottom red into orange without that orange changing. And that's where it becomes tricky, because that orange was entrapped by a green-blue path, this green-blue path. And actually what just happened is that green-blue path got ruined. The green-blue chain is no more. So what could be a situation here? I'm recoloring, so this could actually, so our special red could, oh, what did I do? Can you see I enlarged it? Oh, sorry, I just panicked for a second. So what could happen is that actually by recoloring our red, we are recoloring our orange. And how we would do that? So that red, so we are looking for red-orange path. Actually, that would just be, I like to do the edges in black. That could just be a neighbor of that orange. So when I recolor that red orange, then I would need to recolor that orange red. But it would also be possible, why not, that these two are neighbors. That's an absolutely legit edge. It doesn't cross another edge. So in that case, this newly red vertex needs to change to a newly orange vertex. But then I think you can see where I'm going, because this would be an absolutely valid path. Like it could be an edge. It doesn't cross any edges. And what would happen there is this would need to recolor to red. So that means that I'm still on 4 colors. I changed one of my reds successfully to blue, but I still have an orange, a red, a blue, and a green. So it doesn't work. I think there are a couple more, like there is one more question which would pop into someone's mind. Or at least it did pop into mine, is, okay, so like if this is the situation, now I have all the edges I need. If this is the situation, would it not have been possible that I first deal with the bottom red and only after I deal with the top blue? Because basically our problem is that the green-blue chain that cut off the bottom red from the orange got cut into half. But actually, have a go at it, you can see that it doesn't matter which direction you color or which order you color them. So actually, when the two chains cross, it could go wrong. It doesn't always, but it could go wrong. I'm just thinking, sorry, I was trying to do like as few vertices as possible. I think if like these two could be connected straight away, so I wouldn't need these vertices. And I'm thinking I need at least as many as I have right now on this picture for a counter example. So I'm actually quite interested. Okay, this is a task for you. Not right now, although you can, no, I'm not right now, but if you send in an example, I'm actually quite interested. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I counted them correctly, 10 vertices for this counter example. Let me double check it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Can you put your hands up if you don't think it's 10? Because I just don't want to go wrong. I'm really bad at counting. Okay, so you think it's 10. Oh, okay. Some people don't think it's 10. Okay, I'm gonna count them again. Sorry, I'm quite like I'm a bit. Okay, we have 1. I just don't want to miss one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, I have this one, which is 11. There are 2, and I have the middle one, which is 12. Oh, thank you guys. It is 12. I completely skipped 2. Yes, counting several times. I think like that's where I go wrong. I have 3 dots and then I'm gonna say it's 4. Are we happy with the 12? Well, that wasn't a well phrased question. Can you keep your head up if keep your hand up if you're unhappy with the 12? Unhappy, unhappy. Okay, okay, good. Okay, so 12. So I have a counter example I've constructed with 12. So I think it would be quite interesting. Can you construct a counter example with less than 12 vertices? So counter example. If you do with less than 12 vertices, if you do, please do send it to our email address, which shown as sent in the chat, so enrichment@ukmt.org. Now, this basically concludes a not very successful proof of the four-color theorem, although this proof was alive and was like considered a good proof for 11 years, so that's pretty successful in a way. But actually, what's super surprising, at least to me, is that this wasn't the only proof, only false proof that was alive for 11 years on this exact problem. So this proof was by Alfred Camp, but this other guy, Peter Tree, also had a proof which was also alive for 11 years, and they've disproved by Percy Hewitt and Julius Petersen, respectively. And actually, that's that Petersen with the Petersen graph. So both proofs were alive, both wrong proofs were alive for quite a long time. Now, a lot of people worked on it, and something which is very interesting is Hugo, and I'm not sure how to pronounce it, Hedwiger, has actually made a conjecture, a generalized conjecture, which is still unsolved based on this theorem. So that's been it's unsolved for almost 80 years. So guys, you need to really get yourself together and actually solve it. Somebody will need to solve it at one point, but it hasn't been unproven. So we'll see. And I just realized that I said that the proof happened in the 2976. Obviously, that was supposed to be 1976. It has been proven, the four-color theorem, by Apple and Haken. And actually, what's super interesting in this proof, and I think you might have heard about it, is that it's been done with the help of a computer. Now, we know that it's not enough, like usually computing things are not as good as a proof, because what happens is, like, if you check it for 1, 2, 3, 5, a million cases, just because something works for a million cases, it could still be wrong for like the million and first case. But actually, Apple and Haken did a similar sort of idea as to what Camp did. So we had sort of 5 situations which might be happening. I think they had 1,800 situations that might be happening, and used the computer to analyze all those situations, because that would have been a bit too much work for themselves to do. So they did the manual labor sort of bit, the computer did it, and this guy, John Koch, was the person who helped them with the computer. Now, plot twist, in 1981, Ulrich Schmidt found a small mistake in the code part. Actually, it was very controversial when they came up with a proof that included a code, because people were like, okay, but it's really hard to check the code. What if there's a mistake in the code? Those people of you who do some coding, you will know that like you write a code and it can go funny all sorts of different ways. So actually, Ulrich Schmidt, for his MA thesis, actually found the flaw in the code. Luckily, it got fairly quickly corrected. So the original proof, like a very small modification, is still working. And actually, later in '96, people came up with a better sort of algorithm of doing it. Now, what's the difference between an algorithm and a proof? Is actually like how Apple's and Haken's how their proof goes. It has like a lot of steps of how you can recolor and pick a new color and recolor and do that. So like even if you look at it campus proof, which turned out to be not a proof, you still have to do a lot of recoloring and such. Now imagine that multiplied by a lot of complication. So actually a lot of people worked on it, simplified it, and they have now an even simpler version. Now, what I found quite funny is that these four people, Robertson, Sanders, Seymour, and Thomas, they actually in 2001 announced that they have a like much neater proof as opposed to the original proof by Apple and Haken. So they announced it in 2001, but it didn't get published since then. So possibly there's something wrong with that as well, but they realized it before publishing, which is, I know, I find it quite entertaining. Now, if you want to delve more into the topic, I really recommend just like go to the Wikipedia, either get the book, which is actually, oh, I didn't put the book in. So UKMT has two books on two in the handbook series on combinatorics. One in Introduction to Combinatorics, and the other one is called Topics in Combinatorics. So if you're interested in this area, I really recommend you buy them for the summer. It's quite nice. You can read a chapter. There's a lot of questions and solutions to them, so it's quite fun. It's like BMO stylish questions. And also, if you just want to read more about this, just like Wikipedia, look up the four-color theorem in Wikipedia and just start clicking on links, and it's quite fascinating. And that concludes my talk. Thank you very much for listening. Oh, thank you very much, Shona. It's been linked, so if you're interested, you can have a go at that. I have both of the books, and it's really good. Thank you very much for listening, and have a lovely summer holiday.